So yesterday in class, we went over this example. A bank account is opened with an initial deposit of $120. The account earns a rate of 4% interest. How much money is in the account after 12 years? So we know that it was growth because we have interest. Our initial value was $120. Our rate as a decimal is 0.04. And our time interval is 12. So when I plug it into our equation, we had y is equal to 120, then in parentheses, 1 plus 0.04 raised to the 12th power. So from our warm-up, we watched a video on Desmos. So I want you to go ahead and open up the app, and we're going to use Desmos to help us solve for the exact answers. I just opened up Desmos in my browser, and I'm going to plug in our function. So we had y was equal to 120, and then in parentheses we had 1 plus 0.04. And we had it raised to the 12th power, but for right now, I'm just going to put in x. And when I do that, if I zoom out on my table, on my graph, and I hit so if we look at our graph and I zoom out, we can see our exponential function. And it is growth, like we said, because we are increasing over time. Now, when I have x as my exponent, it shows this graph, and I can plug at any point to see what our value is. So when x is negative 15, y is equal to 16.886. But we know that we want to find out after 12 years. So instead of having x, I'm just going to put in 12. And look, it pops out our answer. It is y is equal to 192.124 if I round it off a little bit. So I can go back to OneNote and say this is about equivalent to 192. So we can use Desmos to help us solve for the answer. So let's see, if I go down to number 2. This is from yesterday also. In 1992, there was 285 cell phone subscribers in New Bedford. The number of subscribers increased at a rate of 60% for the next 10 years. So since we're increasing, we know it's growth. Again, we filled out this table yesterday, so our initial value is 285. Our decimal rate is 0.6, and our time interval is 10. So our function is y is equal to 285 and 1 plus 0.6 in parentheses to the 10th power. So I'm going to switch back to Desmos, and I'll exit out this one and rewrite our new equation. So we had y was equal to 285, in parentheses we had 1 plus 0.6. And again, I'm going to do the exponent with just x, so I'm not putting our time interval in yet. So here in blue, we can see our graph. Now, if I want our exact answer, instead of putting x, I'm going to put 10, and it gives us the answer of 31,336.08. So if I round that to a whole number, it would be 31,336. So I could go back to our notebooks and write that in. So y would be equal to And I can do it with one more example. So yesterday we knew a computer valued at $6,500 depreciates at the rate of 13.6% per year, and it wants to know the value of the computer after 3 years. So since it's depreciating, we know it's decay. We know our initial value is 6,500. Our rate as a decimal is 0.136, and our time interval is 3. So we plugged it into the formula to get y is equal to 6,500, and then in parentheses, 1 minus 0.136, all raised to the third power. So I go back to Desmos, and again, I'm going to plug it in. We have y is equal to 6,500, 1, and now it's minus, because this was depreciating, minus 0.136. And for our exponent, again, I'm just going to put x to start. So look, we can see our graph. If I zoom in a little bit, you can see we are decreasing, which we know we should because we have decay here. But if I want to find the exact value for 3 years later, I'm going to change x to 3 to find out that y is equal to 4,192.32. But again, if I round it to a whole number, it would be 4,192. So I can go back to our OneNote page and write that y would be equal to $4,192. Not dollars, yes, dollars. And if you need the link to the graphing calculator, it is right here. But for classwork, all you're going to be doing is answering all these questions. So you're going to determine the equation, and then you're going to use Desmos to determine the exact value. And each of them will tell you where to round your number to.